Hello, Earth Science, and welcome to our discussion on rocks, or Chapter 6. So we just got done with doing Chapter 5, which was minerals, and now we're going to start talking about rocks. And what is a rock? Well, a rock is a group of minerals that are bonded together. Rocks can be mostly one type of mineral, or they can be lots of types of minerals. We find rocks in the core of the Earth, and we can find them in the mantle, and we find them on the crust. There are three main types of rock. The first is igneous rock, which is formed from the cooling and heating of hot molten rock, which we call magma inside of the Earth. And when it reaches the surface, it's lava. Our second is sedimentary rocks, which is formed by compacting and cementing layers of sediments. Sediments are things like rock fragments, plant and animal remains, and minerals. And the third one is metamorphic rocks, which are formed from the effect of heat and pressure on other rocks, and this kind of switch from sedimentary and igneous to metamorphic. The rock cycle, anytime we see cycle, this is this repeated event where we have this kind of cyclic motion going through here. This is a series through which rock changes from igneous back to magma, back to igneous, to sediments, to sedimentary rock, which goes to metamorphic rock, which can go back to sediments or go to magma. But all rocks at some point in time were magma at their origin. And we're going to start talking about igneous rocks, the ones that are beginning as magma. They have different compositions and textures based on the different types of igneous rock that they are. And this difference is from the composition and the formation of the magma that forms these rocks. There is two main types of igneous rock formations. There's intrusive, which are these things in the ground. And then there's extrusive, which is formed as you have this kind of magma on the surface here. The question kind of to ask yourself here is, does magma cool at the same speed in each place? And the answer is no. At the surface, where there's a lot more exposure to air, we're going to have magma that cools much faster than that magma that's deep inside of the Earth, close to the Earth's mantle. So at the surface, it's faster. Deeper inside, it's slower. So there's two different types of magma. This is the starting material. And there's two different types. We classify it as either felsic or mafic. And we're going to start talking about felsic magma, which is a thick, slow-moving magma. It has large amounts of silica, almost up to 75% here, and smaller amounts of things like aluminum oxide, sodium, calcium, iron, and magnesium. As it hardens, it's going to turn into a light-colored silicate material, things like quartz and feldspars, like that potassium, and it'd be a mix of feldspars and other stuff instead of the pure minerals that we saw in the mineral lab. The second type of magma is mafic magma, which is hotter and thinner and more fluid. It has larger amounts of iron and magnesium, and lower amounts of silica, less than 50%, where the other one was up to 75%. And this is going to form dark minerals like hornblende and augite and biotite. In addition to magma that's at the surface, we have underground magma. This is very deep inside of Earth's crust, and it hardens very slowly. It can take up to several thousand years to harden. The only way we see these magmas as the overlying rock on top of them is worn away, chipped away. We're going to talk about weathering a lot later. This is when this rock becomes exposed to the surface. So with intrusive rock features, the magma that forms these rocks cools very slowly, giving it a coarse texture. As it's cooling, it has opportunity to move and time to form kind of these runs. This creates things like very large, well-defined crystals. We like these well-defined crystals of like quartz and all the quartzes, rose quartz and smoky quartz. At the surface, magma is no longer magma, it is called lava. When lava cools and hardens, it is an extrusive igneous rock happening outside of the Earth's crust. And it can harden rapidly, taking only a couple hours, or in like really deep lava flows, it can take up to a couple days. If it's a really, really deep lava flow, it could take even up to years to completely harden deep underneath the surface there. So with this extrusive process, these particles don't remain liquid long, and because of this, there's not a lot of time for crystals to form. So extrusive igneous rock may have microscopic crystals or no crystals at all. With these tiny crystals, you have a very fine-grained texture versus that coarse texture we've seen earlier. And those without crystals are smooth, and they have like a glassy texture, things like obsidian. So above and below ground, when crystals are forming, they can start underground and then be pushed to the surface. As this remaining liquid cools very quickly, it forms porphyry. And porphyry is igneous rock with large crystals that are surrounded by a fine grained mass of rock. So think big old crystal formation. And then around the edges of it, you have this porphyry, where it's this very jagged kind of pieces there. Another igneous rock is ash. When magma reaches Earth's surface and it's expelled into the air really, really forcefully, it can turn into ash. As ash settles on the surface, if we get a thick enough layer, it gets covered and it compresses to form something called tuff. And even though tuff originates from igneous rock, some scientists call it a transitional rock. It's on its way to being metamorphic. It's on its way to turning into a sedimentary rock. It's kind of this kind of gray area as far as classification of tuff. So when we describe igneous rocks, we group them into families based on what minerals they're composed of. So it doesn't matter where they are, so they can be intrusive or extrusive. It just matters what they're made of. Where these igneous rocks form, whether it's above or below ground, determines their structure. So all of these members can have all the different textures that we can see. In the granite family, these guys form from felsic magmas. They're usually coarse-grained, and they typically contain things like quartz and feldspar, mica, and hornblende. And because they have this high amount of quartz and feldspar, they have a typically hard, they're very hard on the Mohs hardness scale. And with this high amount of feldspar, they range in color from white, gray, to even a lighter pink. Granite is an intrusive rock, meaning it's going to form down here from these intrusions that are kind of going side to side here. So after all of these layers above it are finally removed, then we get to see granite. Where it is very common and where a lot of uplifting has happened very quickly are in mountainous regions. So up here in northern Idaho, we have a lot of granite, a lot of quartz, as these things are being pushed up by these mountain formation processes. Obsidian is a volcanic rock with a glassy texture, has a 5 on Mohs hardness. It's included in the granite family, and it is dark because it has lots of iron oxides in it, or lots of iron mixed with oxygen. Pumice is filled from silica-rich lava that hardened as when it was a steam. Because of this, it kind of resembles a sponge with all these holes in it. And often, your chunk of pumice is light enough that it will float on water, which is kind of cool. The gabbro family consists of mafic rocks. These rocks are darker in color and denser than your granite rocks. They have a lot of pyroxene, olivine, and plagioclase feldspar in them, which gives them a much darker color. This guy's much darker than what we're looking at. It is a very coarse-grained rock and is very dark in color. Basalt is in the gabbro family and is the most common. It is very fine-grained, a dark gray, can be a black, and it forms most of the ocean floor. It is also the most common rock formed when lava flows. And this is where we're finding a lot of it on the ocean floor as we get new ocean floor formed from the flow of lava. Some other gabbro members are diabase. This guy up here is basalt glass, which resembles obsidian, but it's kind of like less fracture-y. It is a mafic origin instead of a felsic. And then scoria, which is like pumice with lots of holes in it, formed from steam, but it's much denser. The atoms in it, the elements in it are much denser. So instead of floating, like pumice does, it will sink. Diorite is neither felsic nor mafic. It kind of has properties of both. It can be a medium gray or green. Diorite has less quartz in it than granite does. This is a nice chunk of diorite. And then andesite is a fine-grained member of this diorite group. Some other igneous rocks, the composition always isn't like you are a gabbro, you are a granite. It occurs in a range. So granodiorite is a coarse grained rock that is between granite and diorite. This is a chunk of granodiorite right here. And it looks a little bit different than both the granites and the diorites we've looked at so far. The igneous intrusions, as we have this pressurized kind of magma underneath the crust, it can force its way between rock layers. As this magma cools really, really deep, this is what forms the cores of mountains. It forms cool intrusions. We're going to talk about a couple of them. A pluton is an igneous kind of intrusion. It is a rock mass that forms when magma cools inside Earth's interior. These guys are only going to reach Earth's surface after uplift and with the help of weathering. There are 5 different types of plutons. There are dikes, sills, laccoliths, batholiths, and volcanic necks. And we're going to talk about each of these coming right up. The first one is dikes. This is the sheet of igneous rock that cuts across rock layers vertically or at a steep angle. This forms when magma intrudes into angled cracks inside of the Earth. So this kind of raised spine here is a dike. Sills. Sills are a sheet of parallel rock that lies parallel to the layer it intrudes. So this is kind of this sill here. This is formed when magma is forced between rock layers, and this is very common down on the Hudson River, over on the Hudson River back east. 3, laccoliths. This is when magma forms really big pools and forms these really nice domed masses. This is a laccolith right here. Batholiths are the largest of our plutons. They form the core of the mountains. So this is a batholith here from the Sawtooths in Idaho. A smaller batholith is sometimes referred to as a stock, and they can be hundreds of square miles big. They're forming the actual core of mountains. They have to be ginormous plutons. And the 5th one is a volcanic neck. This guy here was at one point in time inside of a volcano. This was the magma portion of that volcano. As this volcano stopped erupting, this was left over, and all the stuff on the outside over here got worn away, just leaving this very hard igneous rock behind. All right, now we're going to switch gears to sedimentary rocks. Where igneous rocks form from magma, these guys are going to form through the compacting and cementing of layers of sediment. There are 3 basic types of sedimentary rock. They are clastic, chemical, and organic sedimentary rocks. In clastic rocks, these are formed from fragments of other rock. As you can see in this example here, there's lots of different fragments and chunks of this rock in there. These fragments come from other igneous, metamorphic, or sedimentary rocks. And these fragments can be large as pebbles, gravels, grains, or they can be down to microscopic flakes of clay. Where do these particles come from? Most of these particles are being collected and moved by running water. As they travel in a stream, they bump against other things and they become smooth and rounded. The farther these things are carried, the smoother they become. As these rivers enter a larger body of water, the particles that are large are going to drop to the bottom and be deposited, and the ones that are smaller are going to continue to get moved along. So in the order of deposition, our larger things are going to drop out first and settle closest to the shore, and then our smaller things like sands will do less, will go further, and finally things like silts and clays will go the farthest. So boulders, cobbles, pebbles, sand, silt, and clays. And a lot of earth science is determining things based on their size. In cementation, we're going to take loose particles and we're going to bind them together with natural cements. These are things like silica, SiO2, calcite, calcium chloride, calcium carbonate, and iron oxide, Fe2O3. In cementation, the filling of spaces between sand grains, pebbles, and other rock particles that bind the particles together to form rock. So this process here, where all of these particles have been now fused into one chunk of rock. Our next type is conglomerates, which are our orsic-clastic rocks. Typically, they're a cemented mix of round fragments deposited in rough water. Quartz is a very common ingredient inside of here. You can see little chunks of quartz in there. Breccia is a conglomerate made of angular fragments surrounded by finer grains. So this is some breccia here on the bottom, where they're kind of like these jagged chunks. Almost look like arrowheads that have been kind of just pieced together in there. And sandstones. These are usually made of quartz sand grains. They're rough, gritty, and durable. And up to 30% of it is filled up with empty space, this unfilled area. It is both porous and permeable. As you can see by all these holes inside of it, water could flow through this if it found its way inside of one of these sandstones. Shale. This is formed from silts and clays. It is smooth, soft, and easily broken. This is a whole bunch of shale here that has been broken. And shale particles have no space between them, so water can't flow through it. We say it's impermeable to water. Our second type of sedimentary rock is the chemical rocks. When the water in seas, lakes, swamps, and underground reservoirs is doing its thing, it contains dissolved minerals. As these minerals precipitate or fall out of solution, these chemicals are left behind and this chemical rock forms. This precipitation can form through either evaporation or chemical action, forcing it out of the solution. And some common examples of this are things like rock salt and rock gypsum. Our third type of sedimentary rock is organic rock. And all organic rock are a combination of plant, animal remains, and sediments. So limestone down here, which is all leftover seashells, and coal, which is leftover plants, are formed as they mix with minerals. Now, remember that a mineral is something that is not organic. Rocks can be organic. They can have organic origins and pieces in them because it's a mix of all these things. Limestone formation, as calcite dissolves in water, it turns into ions, these charged particles. Lots of organisms use these ions to produce calcium carbonate shells. Things like all of your sea shells are formed this way. Oysters, corals, clams, and even some algae are other examples. As these organisms die, their shells build up on the ocean floor. And eventually these get cemented together to form limestones. So there's some different features inside of sedimentary rock that we can see. One of them is stratification, and this is the arrangement here of these visible layers. You can see different layers of rock inside of this. This layering is formed as the different types of sediments are being laid down. So each new rock layer here is a new type of sediment that's being deposited. So an example is if we have some sand and it gets deposited on clay, it can cause a layer of sandstone on top of a shale. Another feature is fossils. Fossils is the remains, impressions, or other evidence of plant and animals preserved in rock. So on this top one here, we can see these shells. In these pictures, we can see like the imprint of this fish or this leaf. We can see a whole tooth here from some creature. Fossilization occurs when these dead plants or animals are buried by sediments that gradually turn to rock. As the soft parts decay, the hard parts can be left as fossils. And this is most commonly found in places that were aquatic or swampy when these animals died. Some other features are ripple marks and mud cracks. Ripple marks here on the top, mud cracks here below it. Ripple marks are sand patterns formed by the actions of winds, streams, waves, or currents. If you've seen videos of like the coast, you've seen like as the waves come in, they make these kind of ripples in the sand. If these guys get stuck inside a rock like that, this forms. As that becomes sandstone, that gets preserved in there. Mud cracks are common in roads and areas where you get a lot of water and then no water for a long amount of time. What happens is as this dries out, the space between these guys compacts and it gets mushed together. And we get these cracks forming because it's no longer taking up this whole space. As these get filled in with other sediments, these mud cracks can fossilize. Same thing with these riffle marks. And eventually, as those other sediments get worn away, we can start to see these again. Another feature are nodules, which are hard lumps of fine-grained silica, which is common in limestone and chalk. They can be white, brown, or gray, and if they are called chert. The darker ones, like these ones up here, are going to be referred to as flint. Both forms of nodules were very common in the Stone Age for humans to use as tools and for weapons. They're hard enough that they can be used to break things down, but soft enough that we can form them into kind of arrowheads and spearheads and tools. Concretions are another feature of sedimentary rock. They are these round, solid masses of calcium carbonate, usually found in shale. These form when minerals in a solution or dissolved in water precipitate around shell fragments or other impurities. I think this is our last feature of sedimentary rock is geodes. They're very common in limestone. They can be sometimes lined with these crystals. Usually these crystals are made out of quartz or calcite. As water creates holes in this limestone, these dissolved minerals are concentrated and will start to grow crystals in there, and then as they fill up, they'll seal back over. This one's broken open so you can see what's inside of it. All right, for our last type of rocks, we're going to talk about metamorphic rocks. And these are the ones that are formed from pre-existing rocks, and we call these rocks parent rocks. Because of this, metamorphic rocks will often resemble these parent rocks. So the process of metamorphism is the process by which a rock's structure is changed by pressure, heat, and moisture. The new rocks can differ from their parent rocks. They can be different in composition, they can have a different texture, they can have a different internal structure, or they can have all those things different. There are two types of metamorphism, two types of this process. There is number one, regional metamorphism. This occurs during mountain building movements, and this is where large areas, huge, big old chunks of metamorphic rock form after exposure to intense heat, and since they're underneath the crust here, a lot of pressure. So there's heat from underneath of them and weight from above, and this presses them into metamorphic rock. The degree of this metamorphism is influenced by the amount of heat, pressure, and fluids and or gases to which the rock is exposed. Increasing all of these will increase the degree of metamorphism. Decreasing all of them will decrease the degree of metamorphism that occurs. The second type is local metamorphism, and this is one that's happening in a very small area, and there's two types of local metamorphism. There's contact and there's deformational metamorphism. In contact metamorphism, this is when hot magma moves into rock, heating it and changing it, so things like this volcano over here, things like this coming through this rift here. These hot liquids and gases may enter with intruded rock and react with its minerals. Contact metamorphism causes fewer changes and affects smaller amounts of rock than regional metamorphism. All right, so our second type of local metamorphism is deformational metamorphism, which is happening at a low temperature versus the high temperature ones we've talked about, and it's happening at high pressures. These are caused by lots of stress and friction. So most oftenly we see these at faults, where these areas where these rocks are moving past each other. When we say deform or deformational, this means change shape. So while these rocks usually maintain their same composition, they usually get a different shape. So some metamorphic rock descriptions, they're often based on their parent rock, so they'll have the same mineral content, they can have very similar textures. We'll see foliation, which is the tendency of rock to form bands of minerals. that are split along parallel edges. So this rock on the left here is foliated. Each one of these bands is a foliation. Where this rock on the right doesn't have any of those clear bands, so it is a non-foliated rock. Quartzite. The properties that make quartzite depend on the sandstone that makes it up. It'll always have quartz crystals inside of it. When these quartz crystals are heated and pressurized, the spaces between these grains of sand are filled, kind of the same way that we make glass. This is like a natural kind of process. It is a dense, non-foliated, uniformly crystalline rock. It looks all the same size. It's very dense. It would be heavy to pick up. Marble is metamorphosed limestone. So the parent limestones are mostly made out of calcite. Impurities inside of this is what makes these streaks in the marble. It gives it that really nice, pretty, what we like to see in our countertops. It gives it these wavy streaks and color changes. We usually get marble because of fluids and gases that are causing this metamorphosis. As this limestone gets increasingly metamorphosized, it turns into this nice marble. Shale is something that'll undergo regional metamorphism a lot. It'll have a lot of pressure and heat. This rock will become a lot denser. The grain size will get bigger. The elements will recombine to form mica. And this will cause foliation inside of shale. Slate is a type of metamorphosed shale, but it is the lowest degree. It is the one that has very thinly spaced foliation layers. It's fine-grained and has lots of clay and quartz in it. And it's going to be shinier, flatter, and have a more irregular surface than its parent shale. Phyllite, as we get more intense metamorphism on this shale, we get phyllite. It has this pronounced foliation and a shiny surface because it has lots of these mica grains, which have gotten bigger. They have increased in size. These mica grains are now large enough to see with the naked eye. We can see them well in this picture. Moving forward, we have schists. This is, as this phyllite continues to get heated up, we now have these bands in it as well, this foliation. The parent rocks of this guy are going to be shales and basalts. And they're usually named for the most observable mineral. So they're going to be a mica schist, a hornblende schist, or a talc schist. This is a hornblende schist. And then gneiss. This is one of the most highly metamorphosed rocks. Its parent rocks include granite, shale, and conglomerate. And it is the coarsest foliation with these nice bands inside of these minerals and nice wavy bands. This is the last of our rocks we're going to talk about. This is the conclusion of chapter 6. I hope you know a little bit more about the different types of rocks, sedimentary, igneous, and metamorphic. I hope that you feel confident knowing how they formed, the different ways they formed, the difference between regional and deformational metamorphism, the difference between conglomerate and organic sedimentary rock. I hope you gained more knowledge just about rocks in general, and I hope you have an amazing rest of your day. Thanks for watching.